Okay, so what we're going to take a look at here are a couple of things. First, we're going to look at, in this third video on our introduction to limits, is when limits can't exist. Because we saw, looking at the table with the jump discontinuity, or not in the table, but in the graph from the previous video, which you should be able to see in your notes, the piecewise function, that at certain points, we're not going to have a limit because we're going to approach different values, and that's kind of what we're going to be seeing here. In this function, we have a graph that says at -1, why does the limit not exist? Well, if you look at the limit from either the left or the right-hand side, you're going to wind up with getting different values. So here, I'm evaluating the function as I approach -1 from the left-hand side. And as I approach the function from the left-hand side, I approach a -1 on the y-axis. But if I turn it around and I approach it from the right-hand side, I'm going to see that I approach a different y value, a positive one in this case. Well, because the left-hand limit and the right-hand limit do not approach the same number, this would be an example of that jump discontinuity like what we saw in the piecewise function, and I would say because the left and the right-hand limit do not equal each other, therefore the limit of the function as x approaches -1 does not exist. And if you're curious, those three little dots in the shape of a kind of like a triangle shape, that's how we say the word therefore. That's what the symbol means. So the second type of limit where you cannot have, or type of function where you cannot have a limit, is something when I have oscillating behavior. So here we have some kind of a sinusoidal function, and I would really like to see it kind of expanded out here a little bit, because that's where they're kind of telling us to look, you know, as we approach 0 on the function, what's going to happen. So here again, I'm going to look at it from the left-hand side and the right-hand side, and I'm going to substitute some numbers that are going to be close to 0 on both sides. So as I approach the function on the right side, I'm evaluating it for 0.01, and if I approach it from the left-hand side, I'm approaching it from -0.01. And you see we get a positive value and a negative value for our output. So as I'm approaching 0 from either the left-hand side or the right-hand side, I'm getting different numbers. They're the same amplitude, but they're in a different portion of the graph. One is greater than 0, one is less than 0. So again, the function, the left-hand limit and the right-hand limit do not equal each other. So because the limits on the left and right-hand side don't equal each other, then the function or the limit of the function does not exist as x approaches 0. So moving on, we have our last example of when a function will not have a limit as it approaches a particular value. This is referred to as our unbounded behavior characteristic. So looking at this particular function, this is like the reciprocal squared function. It's just been shifted to the right 2 spaces. So if I evaluate this function at 2 from the left-hand side and the right-hand side, somewhere, there we go. From the left-hand side and the right-hand side, the function both goes towards infinity. So the left-hand limit and the right-hand limit do equal each other. So why am I saying that that the limit here doesn't exist? Well, it's because of what it approaches. It approaches the number infinity. And what is the number infinity? Well, it's not really a number. It's a concept. So we're not actually, we are approaching the same place. We're both going to infinity on the left-hand side and the right-hand side as the limit approaches 2. Unfortunately, we're approaching an extreme. We're approaching infinity at that vertical asymptote, which, it's not a real concept, or it's not a real number. It's simply an abstract concept that we can never actually become. So there's our unbounded behavior as far as why we can't have a limit for that particular function at 2. So the next thing we're going to look at here is kind of like a table, and we can evaluate the numbers in a table to see what's going to happen. Now the function itself could be simplified. I could simplify the function f of x to have an x minus 3 in the numerator, and the denominator would simplify to be an x plus 5 and an x minus 3. And we can see the x minus 3 factor is going to simplify, leaving me 1 over x plus 5. So if you take the 3 and you substitute it into the function itself, you're going to get 0 over 0, which is called the indeterminate form. And of course, we can have a 0 in the numerator, fine. We can get 0 for the number that the function goes to as we approach a particular number. But unfortunately, we can't have 0 in the denominator, or infinity over infinity. That's another kind of indeterminate form. So infinity over infinity like that. But we can look at the table, and from the table kind of see where the limit is going to go. So here it's undefined, because if I put in a 0 in the function, it's going to give me something undefined. But as I approach it from the left-hand side, I can see I'm getting closer and closer to the 3, but without actually getting there. And if I look at it from the right-hand side, and I'm just plugging these numbers into the calculator to see what they give me, I can see that on the left-hand side and on the right-hand side, I get the same value. So I can estimate I can say that even though this is a rational function, that if I do direct substitution, it's going to give me an error, something that's undefined, because we're going to get an indeterminate form. But from the left-hand side and from the right-hand side, we do approach the same value. Therefore, the general limit of the function is going to be that same value of 0.1250. And here you can kind of read this stuff in your notes as you see, or as you want to. This is just giving you some kind of practical way of looking at how limits are going to behave. We know what it should be as we approach that value, but we may not actually get there. So go ahead and read that at your own leisure. The last thing that we're going to look at here is, this is essentially what we were talking about. If the left-hand limit, if the limit of some function as x approaches c from the left-hand side equals the limit of that same function as x approaches the same value from the right-hand side, then the limit, I'm trying not to spell out the whole word, limit of function f as x approaches c will be some number, and that's what they're using, L. And that's all that's saying. If the limits on the left-hand side and the right-hand side don't match, then the limit does not exist. So let me just go ahead and write that down. The limit of the function from the left-hand side does not equal the limit of the function from the right-hand side, then the limit of the function as x approaches that number does not exist. And the last thing that we're going to be taking a look at here in this section of notes is based off of the limit. Can you graph? And this is just kind of reiterating. I'm getting ahead of myself here, but this is what I was just saying on the last slide, is that for the general limit to exist, the left and right hand limits have to match. And so here we're going to try and sketch a graph of the functions as we see here. So I'll go ahead and do one for you. I'll just go ahead and put one up here for you. And so I'll do the one on the left right away. And we have something that looks like this, as f of a is undefined at some point, and at x is equal to a, there's a point of discontinuity, but for the function f as x approaches a, the limit exists. So this is just a sketch. It doesn't have to be the same sketch that you would have created. Go ahead and try doing the second one on the right. Pause the video and try graphing that one. That matches the descriptors and see what you get, and then I'll push play, and then push play again and see what my limit sketch looked like. Alright, so here we have a limit for function f doesn't exist as x approaches a. We have to have a jump discontinuity, so we have a physical break top to bottom at point A, and at point A it is undefined, or at point A it is defined. So here we have our discontinuity. As I go from the left-hand side, I approach a different number than when I approach it from the right-hand side, but I do have it defined because I have some value that when x is a, I do get some corresponding y value for it. All right, so that's going to wrap it up for our introductory limit videos for calculus. But if you have any questions about anything you've seen in any of these 3 videos, please let me know. Until next time, ladies and gentlemen, thanks for watching, and I hope everything is well with you and your world. Until next time, take care.